going to start a unit today on acids and bases. And acids and bases in college chemistry is one of the most difficult units. I don't think you'll find it that difficult at the honors level. We're going to talk about different definitions for acids and bases today. Arrhenius definition, Bronsted-Lowry, and we'll mention Lewis acid and bases as well. We'll talk about some basic properties of acids and bases. And then today we'll also start to get into some very simple calculations with pH. Next time we'll get into more complex calculations, pH, pOH, proton, and hydroxide ion concentration. We'll link that back to stoichiometry, which will be a good review for you. Subsequently, we'll learn how to name acids and bases, such as hydrochloric acid, chloric acid, perchloric, sulfuric, etc. And then finally, toward the end of the chapter, we will learn how to perform acid-base titrations in the lab. When you perform a titration, your goal is to determine the concentration of an acid or a base. If it's an acid-base titration in advanced chemistry, you would do redox titration and other things like that. But titrations are very popular because they're very fun, and they also are informative to determine concentrations of acids or bases. And you'll be doing at least one titration this year, and for those of you who move on to more advanced chemistry, you'll be doing titration quite often. So we're going to talk a little bit about acids and bases, and there are several different definitions for acids and bases, and we'll talk about all of those. We're going to start with the Arrhenius definition. And with the Arrhenius definition in 1887, a Swedish chemist, Arrhenius talked about acids and bases, and his definition of acids and bases is going to focus on which ions are generated. In addition, the solvent will be water. So with the Arrhenius definition, you're going to focus on which ions are generated, and the solvent must be water. Now, both acids and bases conduct electricity, so they must release or generate ions when dissolved. And in this case, we're going to dissolve in water. An acid is going to ionize or generate cation and anion, and the cation must be a hydrogen ion or a proton. So acids, when dissolved in water, generate protons. For example, hydrochloric acid, aqueous, dissolved in water, will generate proton and chloride ion. If the substance generates proton, that substance is an acid. A base is a substance that ionizes in water, but it's going to generate hydroxide ion. For example, sodium hydroxide dissolved in water generates sodium ion and hydroxide ion. If the substance generates hydroxide ion, then it is a base. And again, the Arrhenius definition requires that your solvent is water. But there are other solvents that exist, so this definition for acids and bases really is quite limiting. The other point I do want to make, because this comes up sometimes, bases generate hydroxide ions. Bases, what you're going to have here, metallic cation, hydroxide ion. Be careful there. If you have something like this, that's methanol, which is an alcohol. Bases are things like sodium hydroxide, metallic cation, hydroxide ion, lithium hydroxide, cesium hydroxide. You can have calcium hydroxide, etc. So these are all Arrhenius bases. That's an alcohol. So make sure you have metallic cation in the cation position. The second definition we're going to look at is the Bronsted-Lowry definition. And here your solvent doesn't have to be water. Two scientists working independently, Bronsted and Lowry, define acids and bases in terms of what happens during the reaction, not in terms of what gets generated. So an acid is a substance that donates a proton. When it donates a proton to something else, the acid generates what's known as a conjugate base. A base is a substance that accepts a proton, and when that base accepts a proton, it forms a conjugate acid. Now it turns out that the acid donates the proton to the conjugate base. Acids form conjugate bases, bases form conjugate acids. Now in most textbooks, or if you go online and read about Bronsted-Lowry acids and bases, they will jump right to this reaction and they'll expect you can identify the acid, the conjugate base, the conjugate acid. And the kids always found it very tricky. So let's start a little bit simpler with the following table. One thing I want to show you, for example, if you have hydrochloric acid, this is an acid, and it will form a conjugate base. That conjugate base will differ from the acid by 1 proton. So what you're going to do there is you are going to take away the H and take away positive charge. So this is neutral. When you take away positive charge, 1 minus. That's the acid, that's the conjugate base. An acid is a proton donor. The conjugate base is what you get when the acid donates its proton to something else. So if we work through this table here in regard to conjugate bases, we establish that the conjugate base of HCl is chloride ion. And when you learn how to name the acids, some of this will be a little easier for you because you'll recognize substances as acidic or basic. Hydrofluoric acid. An acid is a proton donor. The conjugate base will lose the proton, so the H is gone, left with a 1 minus charge. If you're initially neutral and you lose plus charge, you have a 1 minus charge. It's like, what do they call that when overdrafting, I think, on your account. So if you have no money and you still pay $1 for something, you're $1 in the hole, or you have an IOU, same thing there. Or maybe a better way to think of it, I don't know if anybody in here plays golf, but if you're initially at par and you make a birdie, you go 1 under par, which in that case is a good thing. All right. If you have sulfuric acid, again, the conjugate base will differ by 1 proton. So you're going to take 1 off. You don't change the number of O's. Initially neutral, now 1 minus. We've got a hydrogen carbonate, also known as a bicarbonate ion. Remove 1 proton. Initially 1 minus, now 2 minus. So what would the conjugate base of phosphoric acid be? H2PO4, 1 minus. Now interestingly, that substance, dihydrogen phosphate ion, can either be an acid or a base. Some substances have the ability to donate or accept. Substances that have the ability to do both are referred to as amphoteric or amphiprotic. Ambi or amphi means both. Somebody who's ambidextrous can write with both hands. An amphibian lives on land and water, so both. If you have H2PO4 1-, that's dihydrogen phosphate ion, what's its conjugate base? Perfect. And water has the ability to accept or donate. In this case, it's listed as an acid. You remove the proton. At first glance, you're thinking HO-, but we don't do ho-ho-hos, so we just do OH-. Hydroxide ion. Ammonia, like water, like dihydrogen phosphate, is amphiprotic or amphoteric. It has the ability to do both. In this case, it's listed as an acid. Shortly, you'll see it listed as a base. Ammonia can donate a proton, and what would it form? Because we're going to be donating, you're going to get rid of one proton in each case. This is acetic or ethanoic acid. That Cu group I introduced you to when you did your drawings early on. You'll be very grateful for that if you do any type of advanced chem. In this particular instance, the ionizable proton, that is the one that will be donated, is the H attached on that Cu group. So you're going to remove, and you're left with a 1- charge. Ammonium ion is an acid. What would be its conjugate base? You got to take away one. You initially were positive, now you're neutral. So acids donate protons and they form conjugate bases. Acids donate protons to bases. Bases accept protons. So when a base forms a conjugate acid, it will have gained a proton. So water will gain a proton and form what's known as a hydronium ion. H3O+ is a hydronium ion. Bicarbonate ion, like some other species we've talked about, has the ability to lose or gain. In this case, it's a base, so it is forming ammonia can act as a base, and it would form typically when you add the H, you add it to the front unless there's an H already there or you have a Cu. So bromide ion as a base forms hydrobromic acid. Hydrogen sulfate ion would form, this would be sulfuric acid, and again, you're going to learn how to name these in a couple days. What about sulfate ion? What does that form? All right, keep going. See if you can do the rest. So you're going to smack an H on at the end. What about this one?
H2PO.
What about this one?
NH3.
What about this one?
HPO.
Easy peasy? Alright, so those are your acids which form conjugate bases, your bases which form conjugate acids. Very straightforward. You'll see some of those on your classwork, also on a little quiz that you'll get next week. Acids and bases react to form conjugates, and they really can be in any order except to say acids and bases are on the left and the conjugates are on the right. So for example, when I'm trying to identify what is what, I look at the first substance and I look off the right side and I see what looks similar. And I can see to go from HCl to Cl minus, this has lost a proton. This is the acid. This is its conjugate base. This base accepts the proton from the acid, and this base forms the conjugate acid hydronium ion. So when I work over here, let's do some type of color scheme. We'll make acid yellow, bases green, conjugate acid blue, conjugate base pink. Sound good? Can you see that? All right, here we go. I look at NH3. I look at ammonium ion. Did this accept or donate? It accepted, so this is a base, and this is its conjugate acid. From here to here, I can see the loss. So this is an acid, and this has to be its conjugate base. This substance looks like this substance. This is going to lose, so this is the acid, and this is the, and therefore this has to be the base, and this has to be the, did I mess it up? I did. What did we say this was? That's the conjugate base. Bad color. This is the conjugate acid. Good. Yes, yes?
Yes.
All right. Try these two. Don't do the next two because I want to show you something. All right. I look here and here. Did this accept or lose? Accepted. So that is a base, and a base forms a conjugate acid. Here's my acid, and an acid forms a conjugate base. Good. I look here and I look here. To go from here to here, did I lose or accept? I lost. So this would be acid, and this would be base. The acid forms a conjugate base. The base forms a. All right, in the next set, I want to show you a couple things because this always proved to be tricky for the kids, but I think I can show you a way that it won't be that challenging. When you're deciding which substance is an acid or a base and you only have reactants, For example, if you had this substance here, and I won't name it yet, in most cases, except two that I can think of, the maximum number of hydrogen is going to correspond to the charge on the anion. So the most H's you can have here is 2. For example, the most H's you can have with a phosphite ion would be 3. So this substance is an acid. It cannot be a base because it can't accept more protons than what the charge on the anion dictates. So this substance is an acid as well. The two instances I can think of where this fails include water, where water can accept a proton to generate a hydronium ion, and the other instance I can think of is with ammonia, where you would think the most would be 3, but it can accept another proton to form ammonium ions. So those are the two instances where the little trick will fail, but I don't think, there probably are others, but I don't think you'll run into them. So if you keep this in mind, I think that will help you when you're trying to determine which substance is the acid and which substance is the base. Sometimes there is more than one answer, so be careful there. So for example here, why must this substance be the acid? It can't have more H's than 3 because phosphate ion has a 3- charge. So if this is the acid, what is its conjugate base? Correct? Okay. And now, here is your base. And now your base forms conjugate acid. And so that's going to form what? Now this last one actually has 2 possible answers. What's the maximum number of protons that a sulfite ion can have? What's the charge on a sulfite ion? 2-. So the maximum number of H's would be 2. So this can either accept or donate, and we already said that ammonia and water have the ability to do both. So there's more than one answer here. If this were an acid, then it would form this conjugate base. If this were the base, then it would form This one, right?
Ammonium.
Ammonium ion. However, if you thought of the equation the other way, where this is the base and this is the acid, then you could have this accepting to form H2SO3, and what would your other substance be? NH2 with a 1 minus. So sometimes there's more than one answer there. And then if this is the base, when it has accepted the proton, you've got the conjugate acid. The acid forms the conjugate base. I tried to make it easier with the colors. I hope so. Alrighty? As I indicated, some substances can be both acids and bases. We refer to them as amphiprotic or amphoteric. Some examples include water, ammonia. We've seen some other examples here. Other examples include things like hydrogen sulfite ion, hydrogen sulfate ion. You can have dihydrogen, phosphate ion, all different types. So very often if you have an H and a charge, it can do either. And there are many more. So we've got Arrhenius acids and bases. We have Bronsted-Lowry acids and bases. I'll quickly mention Lewis acid and bases. I'm not going to assess you on it, but sometimes you don't have protons to donate or accept, but rather you have electron transfer. So Lewis in 1923, this is also the same scientist who came up with the Lewis dot structures, talked about electron transfer. An acid is an electron pair acceptor. A base is an electron pair donor. So a Lewis base must have at least one lone pair of electrons on its central atom. So in the example shown here, if you have boron trifluoride, where you've got boron, and you should recall that boron has an incomplete octet, so you don't have an octet of electrons on boron, and you add it to ammonia, which compound has a lone pair of electrons on its central atom? This one right here, right? Ammonia. So this will be the electron pair donor, and therefore this is the Lewis base. And for those of you who go on to take AP Bio, you'll learn about the final electron acceptor in the electron transport chain. And so if it's the final electron acceptor, then that substance will be a Lewis acid. Not something I'll assess you on here, but there are 3 definitions for acid and base: Arrhenius, Bronsted-Lowry, and Lewis. We also want to mention some properties of acids and bases. Before doing so, in your notes there's a do now, and I think this will be a good place to just practice the Bronsted-Lowry. We'll then get into properties of acids and bases and just talk a little bit about pH today. So try and do that do now, and we will go over it. One of them may have more than one answer. You don't have to give both answers. Tell me when you're ready for the answers. Let's take a look. First one had more than one answer, yes, yes. And the second one only has one answer. This has to be the acid because carbonate ion has a 2- charge, so you can't have more than 2 H's. Easy, easy? The kids usually find this the hardest piece of the quiz. Carbonate ion has a 2- charge, so the most protons it could have would be 2. So this has to be the acid because you can't have 3, so it can't accept more H's. All right, the other piece I would like to mention, 2 other pieces. Very briefly, we want to talk a little bit about properties of acids and bases. Many of the foods we eat are acidic. Some foods we eat are basic. You certainly wouldn't taste acids and bases in the lab because that could be very dangerous. But acids taste sour. So if you had maybe apple slices for lunch, they would have a sour taste. Apple juice is sour. Grapes, what else do you eat that is sour?
Lemons.
Lemons, very sour, and they are very acidic. Children should not suck on lemons. It is awful for their teeth. What else is sour?
Orange juice.
Orange juice, so all your fruit juices.
Strawberry juice.
Yeah, you wouldn't want to be drinking that.
Why not? Sulfuric acid.
Alrighty. Bases tend to taste bitter.
Vinegar.
Bases are like, no, vinegar is acidic. Coffee is acidic.
Why does it taste of bitter?
No.
I don't drink coffee. You can pay me to drink that. Blech.
You wouldn't say sea salt vinegar is bitter?
No, vinegar is acidic. Vinegar is an acid. Bases are like foods that are bases are your leafy greens, things like that. There aren't too many basic foods. Although, if you have an upset stomach and you take like Tums or Rolaids, those are bases because they'll neutralize the acid in your stomach. We'll talk more about that when we get there.
They taught us that. Neutralization.
What? Yeah, we'll talk about that.
We talked about that like earlier.
So your bases taste bitter, but we don't eat many foods that are bases. If you were to feel acids and bases, you certainly would not want to touch a concentrated acid like the 12 molar we used the other day because that'll burn a hole through your finger. But dilute acids like with 0.1 molar concentration, those feel just like water. Bases tend to feel slippery. A lot of your cleaning solutions, like if you clean your shower floor and you don't get all of the base off there, it'll be very slippery. So things like Clorox cleanup, ammonia, Drano, those types of products are very basic and have a slippery feel. If you have curly, coarse hair and it gets clogged in the drain, you might pour Drano down there. That'll really make the drain pipes very slippery. It's also highly exothermic, so it melts a lot of grime in there, and that hopefully will clean your drains, although plumbers tell you not to use that stuff. They say it's bad for your pipes. If you consider how acids and bases react with metals, we have seen and done this before. Many metals will react with hydrochloric acid to generate salts and hydrogen gas. Some substances will not react with hydrochloric acid. If the metal is of lower reactivity or activity than the hydrogen, you'll get no reaction. Bases typically don't react with active metals, so sometimes it's not the greatest test. Both acids and bases, when dissolved in water, do conduct electricity. So you will know a solution is either acidic or basic by doing a conductivity test. You can look at the strength of your solution, but you can't tell an acid from a base by conductivity. There's a couple of little videos here. This one I thought was the best of the bunch. We'll take a look. It goes into very advanced stuff. I just want to look at the pictures.
Acids and bases. Let's start by looking at electrical conductivity.
So what you're seeing here is acetic acid, which is a weak acid, versus hydrochloric acid, which is a strong acid. And we will learn that strong acids ionize completely, and they will be very good conductors of electricity, which you can see by this illuminated light bulb, as opposed to weak acids, which are poor conductors of electricity, and the light bulb will only be dimly lit.
In the beaker on the left, we have a 1 mole per deciliter solution of ethanoic acid. In the beaker on the right, we have a 1 mole per deciliter solution of hydrochloric acid. Ethanoic acid is a weak acid and it partially ionizes in solution. Hydrochloric acid is a strong acid which completely ionizes in solution. As you can see, the bulb on the right is brighter than the bulb on the left. This means that hydrochloric acid is a better electrical conductor than ethanoic acid. So let's look at the reason for this. Strong acids and bases have a higher concentration of mobile ions in solution. Strong acids completely ionize in solution, whereas weak acids only partially ionize in solution. Therefore, they have higher electrical conductivity than weak acids and bases of equal concentration. Next, we look at rate of reaction.
And there are some other videos. One was particularly silly. We'll take a look at them at the end. But in any event, strong acids and bases conduct electricity better than weak ones. There are 8 strong acids. Strong acids ionize completely. Not for the quiz, but for the test, you will need to know your strong acids. You'll see 3 of them are binary, H and 1 other nonmetal. The others are all ternary, H, another atom, and oxygen. And this video goes into strong versus weak in a little bit of detail. We'll take a look.
The strength of an acid refers to the extent that it dissociates into ions when dissolved in water. Strong acids dissociate nearly completely. Weak acids dissociate very slightly. Dissociation into ions means that when an acid, HA, dissolves in water, it transfers a proton to one of the water's lone electron pairs, and the acid anion, A-, and a hydronium ion, H3O+, form. The color change of the water oxygen will make it easier to follow in solution later. The key difference between strong and weak acid dissociation is the final concentration of hydronium ion in solution. Since proton transfer from a strong acid to water is nearly complete, the hydronium ion concentration is essentially the same as the original acid concentration. In contrast, proton transfer from a weak acid to water becomes balanced by proton transfer from hydronium ion to A minus. So the final hydronium ion concentration is much less than the original.
Of those reactions listed there, which one is reversible? This one. So when you have a weak acid, you've got an equilibrium reaction that lies far to the left. So the concentration of the weak acid is much greater than the concentration of proton. With a strong acid, this concentration is going to be the same as this, and that will help us when we want to determine pH of strong acids. So strong acids ionize completely. The reaction only goes in the forward direction. Weak acids show equilibrium reactions, so they don't ionize completely. So there are 8 strong acids, and those are listed. And again, if you have a strong acid, it ionizes completely. For example, hydrochloric acid, you can either just write this way, or if you want to show the water, that is fine. You would indicate then that you have hydronium ion and chloride ion, but the key is that it only goes in the forward direction. If you have a weak acid, such as acetic acid, you're going to have an equilibrium reaction that lies far to the left as such. We're not really going to deal with weak acids at our level this year. We're going to talk much more about strong acids. There are 8 strong acids. Similarly, if you have a strong base, such as sodium hydroxide, your strong bases are your group 1 hydroxides. So hydroxide containing compounds that also contain group 1 ions are strong bases. They ionize completely. Be careful with your 3 strong group 2 hydroxides because they will generate 2 hydroxide ions for every 1 base. For your strong acids, there's 1 diprotic acid. We'll talk about that later, but I'm not going to give you a problem like that because it'll be too tricky. So these are both strong bases. Strong bases ionize completely. And again, your group 1 hydroxides are strong. Your group 2 hydroxides, calcium, barium, strontium, are strong as well. And that goes back to your solubility rules, and those will be excellent conductors of electricity. In regard to indicators, an indicator is a substance that's one color in an acid and a different color in a base. And there are many different indicators that you can use. Some of you probably have used litmus paper previously. And with litmus paper is either blue or red. If you drip acid on red litmus paper, nothing happens. It just stays the same color. But if you drip base on red litmus paper, it turns blue. Base on blue litmus paper stays blue. But if you drip acid on blue litmus paper, it's going to turn red. So it will tell you if you have an acid or a base. Another indicator is phenolphthalein. Oh, you couldn't see my cute little diagram. Oh, I'm so sorry. But I would think you used litmus paper in middle school, right? Yeah. Most of you? One school yes, one school no. All right. Another indicator, and this is a doozy to spell, is phenolphthalein. And phenolphthalein is colorless in acid and pink in base. And we'll be using phenolphthalein with our titration lab. So in an acid, it's colorless, and in a base, it's pink. And what you'll do in the lab is you'll put phenolphthalein in an acid. You won't even know it's there because it's clear. And when you add enough base to neutralize the acid, you'll get a faint pink color. If you add more and more base, then you'll get more like a fuchsia. Another indicator is pH paper. Have you used pH paper before? Some of you? So with pH paper, you dip it into your solution, and then you match it to the color shown here to figure out what the pH is. You can also use pH meters and things like that, and that would be more for advanced chemistry. So those are some indicators you can use. You want to recognize strong acids and strong bases. Strong acids and bases conduct electricity very well because they ionize completely. You want to know some general properties of acids and bases. Make sure you can predict products of Bronsted-Lowry acid-base reactions and identify conjugates and why they are conjugates. So you want to be comfortable with all of those concepts. Questions in regard to any of the definitions or properties? And then phenolphthalein, I can pull up a picture of that. We've done that in the lab previously at the advanced level, and it's something you'll be taking a look at. Next time we will get into pH, which is the power of the proton, and we'll talk about pH in regard to calculating it as well as interpreting it. Questions here? You're good? Okay.